In this lecture, let us talk about the design of sequential circuit using JK flip-flops. The content of this lecture as follows. First, we will discuss the state diagram. Using the state diagram, we will abstract the state table. From state table, we will extract the excitation table. In excitation table, we have a given present state and the next state of the sequential circuit. From the present state to next state, we will extract the inputs of the JK flip-flops. So after further, we will simplify the excitation table using K-map. So after K-map, we will design the logic diagram of the sequential circuit, and in final part of this lecture, we will analysis the designed sequential circuit. Okay. Uh, Furthermore, the design procedure of the sequential circuit usually comprised of the following steps. Uh, First, the circuit behavior description may be accomplished by the state table or the state diagram. So we have given a state diagram, or we will accomplish the uh, circuit behavior by using the state diagram. From the state diagram, we will extract the state table, and then from the state table, we will the state table can be further reduced by using the state reduction method that we will discuss in the coming lecture. If you have a given state table or the state diagram, that can be further reduced. So there is some method which is known as state reduction method. We will use in next lecture. Uh, After reducing the state table, we assign the binary values to the states, to the given state. In next step, we use the excitation table. Then furthermore, the next steps are the K-map. Then after K-map, we design the sequential circuit, and finally we can analyze the uh, sequential circuit by taking into account its working. Now let me start with some example. So we have given a state diagram, and from using the state diagram, we will design the sequential circuit by using JK flip-flop. So here the state diagram. So uh, we have a present state which is 0 0. This is the state diagram. So uh, the present state is 0 0. So this state diagram uh, comprised of input. If the input of the sequential circuit is 0, then the present state would be the next state. So the next state, there are two possibilities. For when input is 1, the next state is 0 1. Further, there are 4 states: 0 0, 0 1, 1 0, and 1 1. So there are 4 states. So these can be described by 2 bits. So for this purpose, the required number of flip-flop would be 2. As already in the previous lecture we have talked about If we have 2 bits, then we use 2 flip-flop. If we have n bits, we use n flip-flop. And with the n flip-flops, the number of states could be 2 raised power n minus 1. So in this case, uh, from 0 to 2 n 2 raised power n minus 1 state. So here we have 4 states. So uh, therefore, the required number of flip-flops are 2. So here we have now present state is 0 1. So the next state would be 0 1 when input is 1. When input is 0, the next state would be 1 0. Further, uh, if we have a present state is 1 0, then for input 0, the next state would be the same state. For input 1, the next state would be 1 1. Now if input is 0, the next state is 1 1. For input 1, the next state is 0 0. So from this state diagram, we will extract, as I already explained, that we will extract the state table. Now the state table can be described as, this is the state table. Wait. In state table, we have a present state, and we have next state. And we have okay, the present state, suppose we have present state is A and B are the present state. These correspond to different bits. So the next state, when we have a zero input, when we have a zero input, suppose x is the input here, variable x I am using for input. So for x is equal to 0 and for x is equal to 1, sorry, for x is equal to, let me change the color. So when x is equal to 0, I will write here the next state. For x is equal to 1, I will write the next state. Now first we'll start from here. Here we have the present state is 0 0. Now what would be the next state when input is 0? The next state would be the same, which is 0 0. Now here we can see when input x is equal to 1, the next state is 0 1, right? Now this is the present state. Now the 0 1 is the present state, and it has again two states depending upon the input. When input is 0, the next state here you can see it is 1 0. Okay, then when the input is 1, the next state is same, there is no change, the next state will remain same, which is 0 1. Now again the present state is 1 0. So there are two, next state. When x is equal to 0, the next state is same as 1 0, and uh, when input is 1, the next state is 1 1. Now we have the present state is when present state is 1 1, there are two next state again. When input is 0, the next state is 1 1. When input is 1, the next state is 0 0. Okay, now using this state table, I will extract the excitation table. So the excitation table will give us the inputs of the JK flip-flop. So let me erase this state diagram. So I will so here I'm going to draw the excitation table. Now in excitation table we have a given uh, present state. So we have a present state and we have input, then we have next state, and from present state to next state we will extract the flip-flops inputs. Flip-flop inputs. So the present state, we know that we have A and B. So the input is X and next state is so the present state I will start from 0 0. When present state is 0, so I'm expanding this state table. When the input is 0, we have next state which is 0 0. Okay, then when the present state is 0 0, input is 1, the next state is 0 1. When the present state is 0 1, so there are two possibilities. Out input could be a 0, it could be a 1. So for 0 1, the input could be 0 and 1. When input is 0, the next state is, we can see here, the next state is 1 0. When the input is 1, the present state is 0 1, input is 1, the next state is 0 1. There is no change. Now the present state I am considering 1 0. So again there are two inputs, could be a 0, could be a 1. When input is 0, the next state is 1 0. There is no change. The sequential circuit will remain on same state. So when input is 1, the next state is 1 1. Okay, when now the present state is 1 1, there are two inputs, 0 and 1. When the input is 0, the next state is 1 1 will remain same. When input is 1, the next state will change 0 0. Now using this present state and next state, we will uh, extract the inputs for flip-flop. So here we have to use the JK flip-flop. The JK flip-flop has two inputs corresponding to A. There are two inputs, JA and KA. So corresponding to B, state B, corresponding to B, so we have, sorry, B is in fact the bit. We have two inputs, JB and KB. Remember the state table. The state table for JK flip-flop, we have already discussed a few lecture before the state table of the JK flip-flop. You guys should keep in mind the state table which we have derived from the characteristics table of the JK flip-flop. Now the state table, excitation table uh, of the JK flip-flop, which was, we have a given present state which was Q of t, and the next state was Q of t plus 1 corresponding to present, and next state we have extracted the inputs of the JK flip-flop. So there were two inputs, J and K. So if we have present state is 0, next state is 0, then we have uh, J must be 0 in this case, and K could be don't care. So from its truth table of the JK flip-flop, when the present state is 0 and next state is 0, K could be 0 and K could be 1, but the input J must be 0. So I am not going to explain this excitation table. Many times I have already explained this excitation table. Now when the present state is 0, next state is 1, in this case J must be 1 and K could be a 0 or 1. When both J and K are 1, then it toggle. I mean, if 0, next state would be a 1. If present state is 1, then next state would be 0. For present state 0, next state, sorry, for present state 1 and next state 0, in this case K must be 1, J could be a 0 and it could be 1. So I will use don't care condition for J, input J. For present state 1, next state 1, in this case J could be a 0 or 1, so I will use input as a don't care. The next state, sorry, and K must be 0 in this case. Now using this excitation table of JK flip-flop, so from present state to next state, I will decide the inputs of the JK flip-flop. Now here we see that for A flip-flop, there we will use two flip-flop for bit A, for this bit for A and B. So first consider the case A. Here we can see the present state is 0 and next state is 0. The present state is 0 and the next state is 0. So when the present state is 0, next state is 0, in this case j is 0 and j is 0 and k is don't care. J is 0, k is don't care. In next case, you see here, this is 0, present state is 0, next state is also 0. In this case, JA is 0, K is don't care. Now again, you see here, when the present state is 0, next state is 1. So here, by using this excitation table, uh, the flip-flops input would be uh, JA should be 1, must be 1, and KA should be don't care. It could be a 1 or 0. There are two possibilities. For this case, when present state is 0, next state is 0. In this case, J is 0 and K is don't care. Now here, taking into account this present state, when present state is 0, sorry, 1, next state is 1. In this case, the J could be a don't care, could be 0 or 1, and K must be 0. So this is the similar situation. J is don't care, K is 0. Again, present state is 1, next state is 1. So J is don't care and K is 0. Now in this, finally, present state is 1 and next state is 0. When present state is 1, next state is 0, keep in mind K is always 1 and J could be a 0 and it could be a 1. So it is a don't care. Now I will consider this B. When bit B is least significant bit, B is taken into account. Here present state is 0, next state is 0. So J would be 0 and K is don't care. So this is the excitation table. You have to keep in mind this excitation table. Now B is 0, present state is 0. For B, present state is 0, next state is 1. In this case, J must be equal to 1 and K could be 0 or 1, so I will use don't care. When B is 1, present state is 1, next state is 0, so the K must be 1 and J could be a 0 or 1, so I will use a don't care here. When present state is 1, next state is 1, in this case K must be 0, J could be a 0 or 1, or I will use don't care. When present state is 0, next state is 0, there is a no change. In this case, J should be 0 and K should be don't care. Next, you see here the present state is 0, next state is 1. So here J should be 1, K should be a don't care. Now here the present state is 1, next state is 1. So in this case, K should be 0 and J is don't care. When present state is 1, next state is 0, K should be 1, must be 1, and J is don't care. Now, this excitation table, I will simplify it using the K-map. Okay, now let me go for K-map. In this K-map, I will use the present state and its input. So this is for JA. I'm going to simplify the input JA, this one input, sorry, this one, the input of JK flip-flop. Now this is BX, and in column side I'll use A. So A could be a 0, A complement, and could be 1. So BX should be 0 0, could be a 0 1, 1 1, and 1 0. So in first case A is 0, B is 0, X is 0. For this case JA is 0. It is obvious A is equal to 0, B is 0, and X is equal to 0. JA is 0. And when A is 0, B is 0, and X is 1, A is 0 here, B is 0, and X is equal to 1. So J is 0. For 0 1 1, when we have 0 1 1, JA is 0. When we have 0 1 0, this is 0 1 0, then JA is equal to 1. So next A is equal to 0 here, 1 0 0, this combination is 1 0 0. Here JA is don't care, and then 1 0 1, this is 1 0 1. For this case JA is don't care. Then next we have 1 1 1. For this condition J is don't care. For 1 1 0, J is don't care. Now we can simplify the input JA. You can see here I can group this one and this don't care. Now the simplified result would be JA would be equal to this column will cancel, A complement will cancel with A, so JA is equal to B into X complement. Now I will simplify the input KA. KA. So here the inputs are for A, and here the inputs are for B of X. So B and X. So this is 0 0 0 1 1 1 and 1 0. A could be a 0 or 1. So here you can see for 0 0 there is a don't care. For 0 0 1 there is a don't care. For 0 1 0 there is a don't care. For 0 1 1 there is a don't care. And then for 1 0 0 this is 1 1 0 0 there is a 0. K is 0. For 1 0 1 this is 1 0 1 K is 0. For 1 1 1 K is 1. And for 1 1 1 0 it is a 1 1 1 0 it is a 0. So from this Kearney map we can simplify this column. We can group these two cells or boxes. Now by simplifying this, this A complement will cancel with the A. So Ka would be equal to K is equal to B and X. This is a B and this is X. Now let me simplify JB. So I will simplify this. 0 0 0 1 1 1 1 0. This is for A, 0 and 1. This is for B and X. So here you can see when 0 0 for 0 0 combination, JB is equal to 0. For 0 0 1, JB is equal to 1. For 0 1 1, here you can see 0 1 1, JB is don't care. For 0 1 0, JB is don't care. For 1 0 0, JB is 0. For 1 0 1, 1 0 1, JB is 1. For 1 1 1, JB is don't care. Sorry. For 1 1 0, this is 1 1 0 combination, JB is sorry, this is 1 1 0. And JB I can write here. This is a don't care. Now I can simplify this Carney map. After simplifying, you can see these 4 cells are adjacent. Now after simplifying this, this column will vanish, and this uh, B complement will cancel with the B, so the JB is equal to X. Now let me simplify for KB. Input KB, so here we have BX along rows, and along column we have A. A could be a 0 and 1. BX have combination 0 0. Then 0 1 1 1 1 0. Sorry, okay, let me erase this. Okay, let me redraw this map. So A could be complement, A could be a 0 and 1. So when we have combination 0 0 0, the corresponding input is don't care, KB is don't care. When we have combination 0 0 1, so KB is don't care. For combination 1 1 1, KB is equal to 0. You can see here, uh, sorry, for combination 0 1 1, you can see here this is equal to 0. For combination 0 1 0, KB is equal to 1. You can see here. For combination 1 0 0, KB is not care. For combination 1 0 1, it is a don't care. For combination 1 1 1, it is equal to 1. You can see here. For combination 1 1 0, it is 0. Now you can see here this, we cannot simplify this Carney map. This is one for combination. So now the KB is equal to, for this cell, okay, yeah, this can be simplified with this don't care condition. By simplifying this, I can write, this B complement will simplify with the B, so I will get X prime, and this is A prime or A complement. So A complement into X complement. By simplifying these two boxes are cells, so this would be equal to, I will write here A into this B will simplify, this B prime complement will simplify with the B, so this is equal to A into X. So these are the inputs for JK flip-flop. Now let me draw the logic diagram. So here we have, let me erase this excitation table. So we have two JK flip-flops. So JK flip-flop has two inputs. I am using here the output. This is A, this is B. I'm not using their complement. It has two outputs. So this is Q, this is Q prime, this is Q, and this is Q complement. It has two inputs. This is KA and JA. So also this flip-flop has two inputs. KB and JB. Okay. Now these both flip-flops have common clock pulse. Let me use some different color for clock pulse. Okay, I'm using the green color for this clock pulse. So this is the clock pulse. These have common clock pulse. Now you can see here the input of JA. This input is equal to B into X complement. So I have to use some external input, which is X here. So this is the external input. This is X and this is X complement. And JA is equal to B into let me use some. Okay, these I mean these wires are not short. So here I will use some OR gate, sorry, AND gate. This JA is B into X complement, B and with X complement. So this output I will AND with X complement. Okay, now KA is equal to B into X. Okay, here again I will use some AND gate, one AND gate. So this AND gate will AND with the B and with x. Now uh, JB is equal to x, which is obvious. So here I will connect, I will not short these wires. It will be connected with the, so now KB is equal to, this can be described with the exclusive NOR gate. So uh, okay, now I will use some, we know that exclusive OR can be described like this. For NOR gate I will use a bubble here. So this is exclusive NOR with A and X. So let me use some different color. Blue, let me use red color. So this wire is not short with this wire. And other input is, so this is the exclusive NOR gate, and the other input is X. So these are the outputs. Now we can analyze uh, this logic diagram. So the given table was like this. Let me erase these K map, Carney map. So let me analyze whether this is working or not. So we have present state, AB is the present state, this is the input, and this is the next state is AB. When the present state was 0 0, next input was 0, the next state was 0 0. When the present state was 0 0, input was 1, the next state was 1 0 1. For 0 1 present state, next state was, for 0 next state was 1 0. Sorry, next state was, yes, for 0 next state was 1 0, and for 1 the next state was same as 0 1. For 1 0, for for 1 0, when the present state is sorry, for 1 0, for 0 the next state is 1 0, and for 1 0, for input 1 next state is 1 1, for input 0 the next state is 1 1 here, for input 1 next state is 0. Now consider some present states. Suppose I am considering here the present state is 0 0. So here I am using input which is x, for x is equal to 0. For x is equal to 0, the next state should be 0 0. So here when x is equal to 0, you see here uh, JB is equal to, for this case JB is equal to 0. So there will be, when JB is equal to 0, there will be no change. So this state will remain same. Uh, Whereas in this case, when x is equal to 0 and a is equal to 0, this KB is also 0. So for JA, we see here it is AND uh, with B and x prime. So this would be also 0 into 1. The AND gate of 0 1 would be 0. So J is equal to 0. This K is B into x. This is also 0. So there will be no change. The state will remain same. So when x is equal to 1, now I'm changing the input. X is equal to 1. What should be the next state? When x is equal to 1, so here this JB is equal to 1 and KB is uh, A into, okay, this KB is the exclusive NOR for A and X. So this is equal to 0. Uh, so the next state, when JB is equal to 1, the next state is equal to 1. So here K, which is AND gate, whose input is AND with B and x prime. So this is equal to 0 when J is equal to 0. So there will be, so the next state would be 0. So next state is equal to 0. Now check some other state. When we have present state is 0 1 and input is 1. So the next state should be 0 1. So here I'm using x is equal to 1. This is the present state. So when x is equal to 1, uh, here JB is equal to 1. So x is equal to 1. This KB would be equal to 0. So there will be no change. The present state will remain same. This J, which is this input is AND with B and x prime. So this would be equal x prime or x complement would be equal to 0. B is 1. So its input is equal to 0. So the K, which is uh, B into uh, B into x, B is equal to 1, x is equal to 1. So when K is equal to 1, J is equal to 0. So the next state will remain 0. Similar fashion, you can, analyze this table. So that's it. So in next class, we will discuss the uh, reduction of the state table. Furthermore, also uh, uh, we will discuss the state assignment. Uh, uh, Now that's it. So next class we will discuss the state reduction by using uh, uh, some mechanism for the state reduction for of the state. We will reduce the state table by using some method of state reduction, and also we'll discuss the state assignment, and we will use some different flip-flop, maybe RS flip-flop, to design the sequential circuit. uh, that's it. Thank you.